So we are now going to compare two populations. And again, this is under sampling and statistics. This is module 10, lesson 10.4. And our learning target, I can use the measures of center and measures of variation to compare two samples and make comparative inferences about two populations. There are several vocabulary words that we are going to be covering. We have asymmetric distribution, double box plots, double dot plots, and symmetric distribution. So I have gone ahead and drawn out a box and whisker plot and a dot plot. We've done box and whisker plots in sixth grade, but just a quick refresher. For box and whisker plots, we basically find the median. But first, we begin by ordering the numbers from the smallest to the largest. And then we find the median, which is the middle number. And if there are two numbers in the middle, we are going to find the mean of the middle two numbers, right? So we find the middle number, we find the smallest number, the largest number, the first quartile, which would be the median of the lower half of the data set, and then the third quartile, which is the median of the upper half of the data set. And so those are the 5 points for us that are required to plot a box and whisker plot. Okay, so I have drawn out the symmetric and asymmetric distributions of a box and whisker plot and a dot plot over here. And data collected from a sample can be organized and displayed in a graph, such as a box plot, a box and whisker plot, or a dot plot. And the shape of a graph is often referred to as its distribution, which shows the arrangement of data values. So in symmetric distributions, the shape of the graph to the left of the center, so this is the center because that's the median, right? So the shape of the graph to the left of the center is going to be the same as the shape of the graph to the right of the center. So that's, as you can see, this is the median, middle value, this is the lower, the first quartile, this is the upper quartile or the third quartile over here. And then we have, of course, the smallest number and the largest number, but you can see that it is pretty much evenly distributed around that middle number, okay? Same thing with dot plots. If I look at this, yeah, this is the center, this is the middle, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 numbers over here, right? So that's definitely falling over here, which is the center, and it's pretty symmetric. As you can see, the left side, the right side, both of those have the same length, as you can see. So that is a symmetric distribution in a dot plot. Okay. Now let's look at the asymmetric distributions. Another thing, like, please remember again, in symmetric dot plots, as I was talking, the frequencies of data values on either side of the center are similar. So you can see 2 and 2 and 1, 2 and 2 and 1. Okay. All right. So in asymmetric distributions, the shape of the graph on one side of the center, one side is very different from the other side because that center is over here. Okay. So please remember that a shorter length indicates the data are clustered together. Okay, so the data is pretty much clustered together in this quartile and over here compared to this. And in the other, while the longer length indicates the data are more spread out. And then in asymmetric dot plots, the frequencies of data values on either side of the center vary. So look, this is the center. Because if we count all this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 20, 23, 24, 25, 26, 27, 28, 30, 31, 32, 33. So this is total amount of 40. So half of 40, which is around 20, which is 20, is going to be falling over here. So now you can see this is the center and or the median, And then look at the graph on the right side and the left side. The right side, they're all clustered together. And the left side, look how long that is. Okay? So that can definitely happen. And let's quickly move over here because I want to show you this. Okay, here we go. So in the distribution shown, the mean is less than the median because the mean is being affected by these outliers over here. Okay, and what is an outlier? Outlier is a number which is way smaller or much bigger than the rest of the data set. Now over here, we have zeros over there, which are less than the rest of the numbers. So that is going to pull the mean down. So if the outlier is towards the lower end of the data set, it's going to pull that mean down. Okay, so as we can see, when we add up all these numbers, and we calculate the mean is going to be 9 and 875,000, which falls somewhere over here. Okay, and the median is going to fall right in the middle over here. Okay, so that's the middle number. And when I'm looking at the mean, it's going to be less than this once again. Because why? Because the outlier is pulling the mean down because it's at the lower end of the data set. Okay, so after selecting the appropriate measure of center, we are going to select the corresponding measure of variation. If you select the mean to describe the center, you are going to select the mean absolute deviation because that is going to show you the variability of the data set. Okay, so let me pull this up like this. All right, so I just want to put that out there for you. So again, when you are selecting the appropriate measure of center, we are selecting the corresponding measure of variation. If you select the mean to describe the center, select the mean absolute deviation to describe how the data vary from the mean. If you select the median to describe the center, we are going to select the interquartile range to describe how the data varies. Okay, so what is interquartile range? It is the third quartile minus the first quartile. All right, so that would be 55 minus 25, and that would give you the interquartile range. Okay, so if we are using median, we would use the IQR. If we are using mean, we would use mean absolute deviation to see the variability of the data set. Okay, for symmetric or asymmetric box plots, you select the median and interquartile range because box plots are constructed to display these values. Okay, now let's go ahead and look at this, and now we are going to start comparing two populations. Okay, so I am going to pull this up. So let's look at this. Two different populations that are provided to you, and a double box plot, it consists of two box plots graphed on the same number line. These are two box plots that are graphed on the same number line. Okay. Hold on. Sorry, I'm trying to make sure that you can see properly. All right, here we go. And then a double dot plot consists of two dot plots that are constructed so that the values on each number line align. Okay, so this is 0, this is 5, this is 10, this is 15. So that's what it means, that the values of each number lines align, but then there are two dot plots that are together like this. You can draw inferences about two populations represented by a double box plot or a double dot plot by comparing their centers and variations. Okay, to select the appropriate measures of center and variability, to compare populations in double box plots or double dot plots, check for symmetry in each data set. Okay, so in symmetry, both sets of data are symmetric. Okay, so both sets of data will be symmetric. The measure of center can be mean or median. Measure of variation can be mean absolute deviation or interquartile range. If it's there's neither set of data, if neither set of data is symmetric, then you're going to select the median and use interquartile range. If only one set of data is symmetric, then you're going to use median and use interquartile range. So if neither data is symmetric or only one data is symmetric, then you're going to use median and interquartile range, okay? And then if both sets of data are symmetric, then you can use mean or median, and then you can use either mean absolute deviation or interquartile range for that measure of variation. Okay, so let's look at this, and we are going to use the measures of center and variation to compare the two populations. And then you're going to refer to the double box plot shown. So, what is the median of the top box plot? So, median means the middle number. The top box plot is here. Median is the middle over here. This is the median of the top. This is the median of the bottom. So, if it's asking for the top, what is this? This is 35. So, the median of the top would be 35. Median of the bottom box plot is going to be 15. Okay, how do the centers compare? The median of the top box plot is more than twice the median of the bottom box plot. So as you can see, this is 15, this is 35. More than twice, because twice 15 would be 30, and that is 35. So that's why it's saying more than twice. Okay, what is the interquartile range of the top box plot? So interquartile range is the third quartile minus the first quartile. And if I do 40 minus 30, I'm going to get 10. And that is my interquartile range. Let's look at what is the interquartile range of the bottom box plot. Okay, so for the bottom box plot, I have 20 minus 10. So the interquartile range over there is also going to be 10. And how do the data in the populations vary around the median? Because the interquartile ranges are the same, the data are similarly clustered around each median, although the medians are different. So the medians are different, but the way the data is clustered is pretty much similar in both the box and whisker plots over here. Okay. What else do we notice about these two populations? Okay, so while the IQRs are the same, the longer whiskers in the bottom plot, okay, so these are the whiskers. So the longer whiskers in the bottom box plot indicate the data are more spread out near the extremes than they are near the center. So it's more spread out near the extremes over here. Okay, so that's another thing that we can look at that graph and discuss. All right, so let's compare two populations now. And you're going to look at this. We have these two populations. And we are going to look at these dot plots. And this shows the heights in inches for the girls and boys in Imani's math class. Okay, so use the measures of center and variability of this sample to make an inference about the heights of students in Imani's grade at school. So we are going to compare the measures of center, and then both the dot plots are symmetric. You can, because they are both symmetric, you can use either mean and mean absolute deviation, or the median and interquartile range For this example, I am going to go ahead and calculate the mean. So if I'm looking at this, I have on the top one, okay, because I have to like look at the girls, I have to look at the boys. So in order for me to calculate the mean, I'm looking at, okay, I have 160, I have 61 times what? 3, right? Then I have 62 times 4 plus 63 times 3 plus 64 times 1. Okay, so this is, we are trying to calculate the mean height of the girls. And then a total number over here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I divide by 12. And when I do this calculation, I'm going to get 744 over 12. And so the average height of the girls is going to be 62 inches. Okay. Now, if we look at the boys, same thing. We're going to see, all right, we have one boy that is 63 inches. Because remember, when we're calculating mean, we add up all the data set and then we divide by how many data values or entries there are. Okay. So now we have 64 times 2 of them plus 65 times 2 plus 66 times 3 plus 67 times 2 plus 68 times 2 plus 69. And then we are going to divide this by how many boys there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Divided by 13 boys to find the average height of the boys. And I get 858 divided by 13. And that gives me the average height of the boys to be 66. So this is the average height, 62 inches, and that is 66 inches for the boys. The mean height for the boys is 66 inches, and the mean height for girls is 62 inches. And then for each mean absolute deviation, we are going to find the mean distance from each data value to the mean, okay? And when I calculate the mean absolute deviation of this one, okay, I'm going to get 2 plus, let's see, 2 plus 3.1 plus 4 plus 3 times 1 plus 2. And so for girls, my mean absolute deviation when I calculate, okay, I am going to get 0 and 8300th. Okay, because we are trying to see how far each number is from that mean. And so this is for the girls. And to find the mean absolute deviation for the boys, mean absolute deviation for the boys, I am going to see, because in the first one, the mean was 62, please remember. Okay, in the first one, this is the mean. So we are seeing how far is 60 from, how far is 61, how far is, so that's how we are comparing the mean absolute deviation. In the second one, the mean is 66. Okay, so how far is 63 from 66? How far is 64? How far is 65? 67, 68, 69 from that, which is 66. All right, and so when I do that calculation, I get 18 over 3 when I add all the mean absolute deviations, and I get 1 and 3800. Okay, so when I look at this, I can make inferences that the mean height for boys is greater than the mean height for girls. Because if I look at the two, look at the mean absolute deviation here. So I know that 1 and 3800 is greater than 8300. We're looking at the variability of the data set, okay, when you're doing the mean absolute deviation. The girls' heights are more closely clustered together than the boys' heights. And when I'm making an inference about the heights of students in Imani's grade at school, based on these samples, you can infer that the boys in Imani's grade are generally taller than the girls. And this inference is based on these samples alone. Different samples may lead to different inferences about the population. So this is basically just for this school. Okay. Now, can you make any other inferences about the heights of students in Imani's grade at school based on these samples that I have over here? Okay, so yeah, sure, because some of the girls and some of the boys were the same height, I can infer that this is likely true of the general population also. All right, this is likely true. So now let's do a quick check. And let's look at this. And we're going to look at Cam and Logan record their resting heart rates each morning for 10 days. The double dot plot shows the heart rates in beats per minute. Use the measures of center and variability of these samples to select the person or persons to which each statement applies. So I have certain statements, and then here I have the heart rate, beats per minute. All right. So if I look at the first statement, and it's saying that the mean heart rate is 65 beats per minute. So let's see, for who is the mean heart rate 65 beats per minute, and here. Okay. And so that would be for Camden. The dot plot is symmetric. Okay, so which one has a symmetric one? Both of them are symmetric. Okay, because here, look, this is the middle, and then both sides same thing, middle, and both sides are the same. So both Logan and Camden have symmetric dot plots. This person is likely to have a higher heart rate on a randomly selected day. So let's look at both of them. The heart rates are higher here compared to this value. So we would say Logan is likely to have a higher heart rate on a randomly selected day. Okay, which data has greater variability? And this one, because this is clustered more together in Camden's case, but in Logan's it is more spread out. So that data is going to have more variability. This person is most likely or more likely to have a heart rate of 65 beats per minute on a randomly selected day. So for 65 beats a minute on a randomly selected day, we don't see any for Logan over here. So this definitely, because this is where the majority is, and your median is also over there. So we know it's going to be Camden for this situation. Okay. Um, let's do comparing two populations again. And the double box plot over here shows the number of daily participants for two adventure companies. Okay, so as you can see, you have Rapid Adventures and you have Whitewater Tours. So compare the measures of center and variation. So let's look at this. And I am going to use interquartile range this time. I'm going to find the median, and that will be another way to do this. Okay, so the distribution for one company, which is like Rapid Adventures over here, uh, is asymmetric, and it definitely contains an outlier, which is being shown over here with that asterisk. Okay, so the median and interquartile range are the most appropriate because it is asymmetric. It contains an outlier. So therefore, because of that, the outlier, it's better to use the median and the interquartile range. Okay. Now, so we're going to find each median. And if I look at this one, what is the median up here? Is 70. What's the median here? That is 50, just by looking at that. Okay. And then I'd find the interquartile range, okay, which is going to be for the top one. Um, we know that interquartile range is the third quartile minus the first quartile, right? So remember, here's the median. That's the middle. That was 70 over here. And the median over here is 50. Okay. The interquartile range. So this is the third quartile. This is the first quartile. So that would be, this is what? 80 minus this much, which is 50. And so the interquartile range of the top one, which is Rapid Adventures, is 30. Okay. And then the interquartile range of Whitewater Tours, this is 60 and this is 40. So subtract Q1 from Q3. So that means 60 minus 40. And I get 20 is my interquartile range of Whitewater Tours. So the median number of daily participants is greater for Rapid Adventures than Whitewater Tours. And there is greater variability among the data for Rapid Adventures than for Whitewater Tours. Okay? The data are more closely clustered around the center for Whitewater Tours. So again, you can really see the variability among the data over here just by calculating the median as well as your mean, what do you call it, the interquartile range. Okay, so when I'm making an inference about the population of daily participants for the two adventure companies, so I can look at this and then I can, based on these samples, you can infer that on any randomly selected day, it is likely that Rapid Adventures will have a greater number of daily participants. Okay. However, the number of daily participants of Whitewater Tours is more likely to be consistent because it's more clustered together. Okay. So this inference is based on these samples alone, and different samples may lead to different inferences about the population. Okay. So let's go ahead and do one last problem. So let's look at this as the last slide that I want to share with you. The students of a middle school start a blog for the English class and contribute to it all year long. The double box plot shows the results for how often 7th and 8th grade students contribute to the blog. So use the measures of center and variability of these samples to select all of the statements that can be inferred about the data. Okay, so let me pull this down so we can look at a few. So let's look at the data over here. All right, so the first one is saying the students in the 8th grade posted blogs more often than students in the 7th grade. Okay, so you can see the blogs over here. Here's the median, which is higher than over here. This is clustered more over here. So yes, this is correct. Okay, so definitely we are going to use the median and the clustering of the graphs, the box and whisker plot. So it's saying students in the 8th grade posted blogs more often. Yes, they did. Absolutely. The student in the 7th grade posted blogs more often than students in 8th grade. No, they did not. They have less. Okay, then the amount of variability for 7th graders is greater than that for eighth graders. So yes, seventh graders have more variability in the data set. Look at the way this is falling compared to it being a little bit more symmetric and clustered here. This is pretty spread out. Okay, so the variability is higher. And then yes, we do have the whisker longer too. So most of the data like over here is centered here, not in this case. This left is less, so it's skewed right. So distribution is more skewed right. Okay, so every student in eighth grade posted more blocks than every student in seventh grade. And that is not true just by looking at this graph. Okay, then 25% of eighth graders posted at least 25 blogs throughout the year. Okay, so eighth graders at least means minimum 25 or greater. Now, if we remember box and whisker plot, it doesn't matter what the length of the whisker is or the length of the from the first quartile to the median, or the median to the third quartile, and then the last whisker. It doesn't matter what the size is. Each of them contains 25% of a data set. So this contains 25%, 25%, 25%, 25%, or one fourth, one fourth, one fourth, one fourth. All of them are containing that much of the data set. Okay, so if it's saying at least 25 blogs throughout the year, that means 25 and higher. So 25 and higher. So yes, that is absolutely correct. Okay, so basically, again, this lesson, as you can see, uh, we could just look at the kind of distribution and then use the method of choice, whether we are using mean or median and interquartile range, and mean or mean absolute deviation, in order to look at the spread of the data, and then to find the variation and compare two samples, so that we can make inferences about the populations. And that would end our lesson 10.4, and we will do the last lesson in this unit tomorrow. All right, have a great day.